Hello everyone, my name is Michał Maciejewski, and today I have a great pleasure to speak on behalf of a great team about a great project which is called STEAM, and in particular about application of Java technology to the project we are developing. And it is quite a recent project which puts a lot of emphasis on building a competence in coupling of optimized simulation tools for the simulation of transient effects in accelerator magnets. And speaking about that, actually recently I've seen a very nice movie which is called The Bridge of Spies, where Tom Hanks plays a lawyer defending a Russian spy caught in the United States during a Cold War, so it was quite interesting period. And he's negotiating agreement between Soviet Union and the United States to exchange the spies, so it's quite interesting. And now looking behind the scenes, actually what we do in real life, because coupling term itself is quite overloaded. So what we do behind the scenes, we couple dedicated hardware. So if you want to display a movie, we go for a projector, which is a separate device, audio system, and a text processor in case you would like to play subtitles. And all that is coupled to a computer that is sending information to all of them in a one way. So actually in life every day, we perform one-way coupling. And now let's ask ourselves, how does it translate to accelerators? And let's recap a bit, because there was a nice keynote in the morning. Accelerator is like a swing, okay? So we can swing the particles inside. And here we have superconducting magnets, which are covering the entire circle of the LHC, which is 27 kilometers. And they are guiding particles to be kept inside the trajectory, and then electric field at some point to accelerate them. And now if we cut a magnet somewhere in the middle and we look inside, we will observe that there is a straight field which is perpendicular to the direction of the motion of particles, and that altogether creates a Lorentz force that would bend the beam. And now if we see as the beam emerges from the screen, it also moves a bit to the right, so it's bended. If we now put it into the accelerator, it will be bended with the magnets until it reaches the accelerating cavity, gets a kick, and runs around. And okay, so now we know the principle, and let's consider the implementation of that. So the principle stays the same. However, we need to build a highly sophisticated structure around it, which is as precise as a Swiss watch, maybe this one as we can see here. But the Swiss watch that weighs 20 tons and is 15 meters long, we need to operate at superconducting state in order to generate the high magnetic field, which is, the magnet is cooled by superfluid helium up to 1.9 Kelvin, so some minus 270 degrees. And these topics are anything but easy, and were awarded several Nobel Prizes for the research. So it is quite a complicated machine, and we have 1,200 magnets like this, which are powered with a dedicated circuit. So we have a certain current in the magnet, and for that we have a dedicated controller that shapes the current in the circuit, that then powers the magnet and gets the desired magnetic field. And this magnetic field has to follow the particles that travel up to the speed of light. And yes, the current in the magnet is 12,000 amps, which is equivalent to 600 households. And this current, together with high magnetic field, is creating or is responsible for very high energy, which for a magnet is like a 20-ton truck traveling at 95 kilometers an hour. But for the circuit composed of 154 magnets, is already something like TGV. And we need to carefully study these magnets for the safety and maintenance of the machine, as well as research and development. And in our group, we are responsible for both tasks. For today, which is the operation of the LHC, for tomorrow, high luminosity upgrade of the LHC, and the day after, which is future circular collider. And of course, with great power comes great responsibility. And if we do not manage the energy well, and unfortunately it happened already in the LHC, there was a damage that stopped the operation of the accelerator for 1 year. And therefore, we really need to understand what happens in these very complicated devices. The damage potential is huge, and without simulations, we cannot understand the behavior of the magnets. Okay, so now let's see how we operate. So in normal operations, as we already learned, we only need a circuit and a controller. So if you want to simulate the two, actually, there is no one-size-fits-all. That's the whole purpose of simulation coupling. We have a dedicated tool for a circuit and a dedicated tool for the controller that has to communicate with one another. And here, let's just consider that the circuit itself spans from meters to kilometers. So I think the LHC main dipole circuit is 7 kilometers. And the phenomena occurring inside are from milliseconds to minutes. So we need to carefully consider these phenomena occurring in the simulation tools. And that's normal operation. However, at some point, there could be a quench. A quench is a transition from the superconducting state to the normal conducting state. And superconducting state is usually described by certain current density, magnetic field, and temperature. So as long as we are under the surface, we are in nominal operation and we are good. However, if there is some energy deposition somewhere in the magnet, misfunctioning of a powering system, misfunctioning of a cooling system, we would quench. And if that's the case, it usually happens at a very small spot. We need to understand how it propagates. So we have 1D models which propagate, and then we see whether we will run away and build up more and more temperature in a very small spot, or we will recover and we can keep operating. If we do not recover, we detect a quench, we have to protect it. And here the principle is quite simple, because we need to do something like with clapping of hands. So if we clap, then we don't hurt ourselves. But if we put a needle inside, in between our hands, and we clap again, well, we will not clap. So again, the quench is the same thing. If we have our energy located at a very small spot, and we discharge it all inside, we'll damage the magnet irreversibly, and we'll have the same situations as several years ago. So what we do is actually something counterintuitive. We apply protection methods to quench as much volume as possible, so clap hands without needle. So one thing is to study the thermal response. The other is to study magnetic field response during the discharge, because both of them are affecting the mechanical structure of a magnet. We have thermal contraction. As we hit something, it expands, but we have also Lorentz force. So current and magnetic field is creating a force that is acting on a coil. And this we need to study, especially in case of upgrades where we are going towards higher performances. So we need higher accuracy and high fidelity software. And now comes a big challenge of our group, because here we have distributed models, so that resistance is distributed over the surface. Whereas for a circuit, the resistance is a one parameter. It can be 5 ohms, 10 ohms, or 1 milliohm. So now the challenge is how to translate something that is distributed geometrically into a circuit, how to distribute the magnetic field properties into a single parameter and still be able to follow the process inside the circuit. And these are the challenges we are tackling with this team, as well as the challenges of various scales. So we're talking about kilometers, but what happens on the origin of the quench is micrometer scale, microseconds time resolution. So the problem is sort of governed by multi-tree, multi-physics, multi-scale, and multi-rate. And this is non-trivial task. There is no tool on the market that can handle all of them together. And for that, we put a lot of effort to create Steam every day and also every night. So yeah, the key question is how we can couple the two. And let's focus on a simple example. We have a magnet which after quench is building temperature. So we have certain resistance that we have to translate into a circuit. But circuit, seeing this resistance, will decrease the current, right? The resistance for electric circuit is like a breaker. So we will have a decrease of current. And for that, we have two models because they are incompatible. We cannot run them together in a monolithic sense. So we run circuits separately. We obtain information about current. We plug it to the magnet. We run magnet now. We get information of the resistance, and we put it back. Of course, if we do it only in one cycle, we cannot guarantee the convergence. And for that, we need to iterate. So we start with our initial guess of resistance, which is 0. We get the current profile. This current profile is passed to a big model of a magnet. We get a resistance. Resistance grows, so in next step, we will have larger current decrease because we have more resistance. But as the current is decreasing faster, we will, in this iteration, build less resistance. So now less resistance means a bit more current and a bit less resistance. So we iterate and we play this game until we find a convergence. And here actually after the next iteration, the two curves overlap. When you can call it a day, we are done, we converged. So in general, what we need, if you want to make the two feel the same phenomena, is to iterate. And in general, the more iterations we do, the better accuracy we get. Looking at the example for the future circular collider, which is supposed to have something like 100 kilometers in the area, so it will have Salev in the middle and it will go under lake, we see that indeed we discharge the energy stored in the magnet in less than half a second. That's mandatory. If we do not discharge the current in this time, we destroy it irreversibly. So we see the current discharge, we see the resistance growth. So this is what circuit sees, but that's actually, this resistance is a result of this temperature profile inside the magnet, which is, again, a consequence of triggering the protection system. So these are the complexities we are dealing with. This is something we have to capture, and for that we have chosen Java. And at the early stage of the project, we have a very nice collaboration that lasts till today with our software team of MP Group. We are receiving a lot of help because by degree we are mostly electrical engineers, but we are doing software. And for that, we started with defining some sort of decalogue of good coding conventions. That was a very first step. And then on the way, as we decided to go for Java, we are receiving a lot of help defining some integrated development process with the tools I probably shouldn't explain here because you know it best. And yeah, what do we appreciate about Java in this particular application? It's first of all available APIs, so we can build our models automatically. It is a mature technology, it's a well-established technology with a great deal of available tools. We have huge expertise inside CERN, which we highly value. We can turn with any question to experienced colleagues that can help us and tell how we should do things. Maybe there is a design pattern. Actually, we implemented quite a few, like state machine, factory design pattern, static factory. And all that made us possible, lets us implement some sort of object-oriented modeling. So we can describe our models as objects and create one-to-one link between reality and code, because our main objective is to bring this physical description, bring math to code. And with object-oriented modeling, we can do it. And something recent, and what one of our colleagues appreciated a lot, and so do we, is with Java 8, the use of Lambda functions. One thing that is not yet clear for us is how to script in Java, because always we need to compile the code, so maybe if you have any ideas, we can discuss it over coffee. And why do we need to script? Well, actually, our main objective is to let user of this team, because it's not only for us, it is for the community of superconducting magnets, focus on the task. And his task is not to build model over and over again, but it's to define input, create model automatically, analyze output, and maybe make several cycles, but focus on the task at hand. The time spent on building the model by hand is the time wasted. So no matter if we create a geometry like this, when we need to define it from the very beginning, like at the high school, we have to define point, lines, areas, or a circuit that would have around 10,000 elements, all have parameters, all have special physics properties. For that, we have a single recipe, which takes the user input, passes it to Java model generator that either triggers a geometry module, so it builds geometry, defines physics over it, defines mesh properties, or a topology module that takes the input describing the circuit and creates the corresponding model. So all that creates a magnet model, and then we can link it with our custom libraries that can represent a magnet, a power converter, an energy extraction system, and so on. So that is at the level of automated model generation. Now if we move to the co-simulation interface, getting to the end of my talk, actually, what we implement is the state machine. So if we remember what we discussed, actually, normally we start with a controller and circuit, and we can move on like this to the end of the run, which is a nominal operation. In case of quench, we need to study the quench propagation, and either we recover or we need to detect it, and then follow this path by performing magnet circuit coupling to see what's the peak temperature, up to the circuit study after we discharge the magnet and the circuit discharge. We can also go directly from controller circuit and the field circuit coupling. But here the main message is that actually if we couple model together, we get more than each model can do on its own. So we have some sort of synergy here. And to me and our team, STEAM is also simulated together. Everyone achieves more. And building and bringing that all together, the STEAM can be seen as some sort of abstraction to simulation software. So on one side, we have here automated model generation, so we create magnet, circuit, and controller models. And we can already see that this is sort of horizontal scalability because we can plug more and more and more. It's meant to be general. Then we have general model adapters that treat models in general terms, so we can run these models, get output, set input, and so on. And finally, on the top, there is also expertise of the user. So he defines the co-simulation scenario, he knows what models to bring together. And we think that that's a sustainable solution. Of course, this architecture is supposed to be refactored on the way, but we believe it is a good image. And to conclude, as I started with a movie, I will finish with a great book of Alan Lightman, which is Einstein's Dreams. This is a book with a set of chapters, the dreams of Einstein, so something that Einstein could have been dreaming when he was developing a relativity theory. And these are our co-simulation dreams. So first of all, we put a lot of effort to build optimized models, and we have consistent physics modeling. By means of efficient coupling interfaces, we gain performance. The approach itself has immanent modularities, which supports the maintenance and expandability. And here, what is clear to state, it's important to state that we are not the only guys that know how to couple things and how to model magnets. No, we are open to other contributions. And finally, last but not least, accuracy of results with this approach is a function of available resources. So it's a function of license, computing power, or time. Of course, I am aware, and we are aware, that making these dreams come true is a challenge. However, with our great team, impossible is nothing. Actually, this team, as we call ourselves, or CERN in general, because we have really multiple collaborations. Thank you very much for your attention. It was a pleasure for me to be here. If you have any questions, I'll be happy to answer.